Okay, this is an example that was actually in the notes, and in the slides of the notes, but I just wanted to go through it again and just expand on it a little bit. So we have an equation, x squared plus y squared equals 25, which is the equation of a circle centered at the origin of radius 5. So here's the graph of the circle, there's the equation. So the idea with implicit differentiation, again, is this, that even if you take a curve that's not a function, there are still points on that curve, and there are still tangent lines on the curve at those points, and we would like to be able to compute the slope of those tangent lines. So again, how do I find the formula for slope when I don't have a function? Well, I just take the derivative of the equation, and again, it's easy to do once you've done a couple and get kind of in the habit, but again, the process is, regardless of where there's x's and y's in the equation, we just take the derivative of everything. We take the derivative of both sides with respect to x. Okay, so here what I'm going to do is take the derivative of the left side with respect to x and the derivative of the right side with respect to x. And again, as I said in the notes, the only thing that's different is when you take the derivative of y's, okay, terms with y in them. Okay, then you have to remember to treat y like a function. Okay, so how would I go about doing this? Well, all the rules of derivatives we've talked about still work. For instance, on the left, I have the derivative of two things added together. So I can take the derivative of the x squared and add that to the derivative of the y squared. Okay, so just the sum rule still works here. And over here I've got the derivative of 25, which of course I can answer that question right now. The derivative of a constant is 0. Okay, so what about the derivative of x squared with respect to x? Well, nothing's different than what we would have done in the past. We're taking the derivative with respect to x of the variable x squared. So it's just the power rule. So that derivative is 2x. Okay. Now this is the different one. We're taking the derivative with respect to x of y squared. So we don't use the power rule here, we use the generalized power rule. Okay. We treat y like it's a function. So we treat this expression as if it's some function squared. And the generalized power rule tells me that when you take the derivative of a function to the power 2, you bring down the power, okay, you decrease it by 1, so I've got 2 times y to the first power, or just 2y. But then we have to multiply by the derivative of y, okay, right? We have to multiply by the derivative of the thing we were squaring. That's the generalized power rule, okay. Now we didn't have to do that over here because we were taking the derivative with respect to x of x squared. Okay, that's the power rule. Here, though, it's the generalized power rule. Okay. Now, you can call this dy dx or y prime, whatever you want, but it's the thing that we're looking for. It's the derivative of y with respect to x. Now, normally, when we have a function, which is an equation solved for y, we already have dy dx on one side. Okay, but we actually need to solve this for dy dx. That thing is the derivative. We'd like to write that in terms of x and y. Okay. So the last step to do is to solve this algebraically for that symbol, dy dx. And remember, that is a symbol. You can call it y prime or dy dx, but it's just a single thing here. It's the term we want to solve for. So I subtract 2x from both sides. I'm just trying to get this symbol by itself. Okay, I get 2y times dy dx equals negative 2x. Okay, and to get the dy dx by itself, I just divide both sides by 2y. Okay, that will cancel the 2y factor over here. And I get dy dx, okay, the derivative of y with respect to x is negative x over y. Okay, now, so I'm going to erase my work now and just focus on this thing. Okay, this formula, dy dx equals negative x over y, it's just a derivative. It tells me the slope of points on this curve. Okay. Now the difference is, since we started with an equation instead of a function, generally when you compute an implicit derivative, it will depend on both x and y. Now for a function, if you tell me the x-coordinate of a point, I can find the slope at that point on the graph. But here I need both the x and the y-coordinate. Okay. So how does this formula work? Well, if you find a point on the circle, we can compute the slope of the circle at that point. So as an example, one point which happens to satisfy this equation is the point right here, 3, 4. You can check that when x is 3 and y is 4, the left and right sides are equal in this equation. Okay, so that's a point on the curve. There's certainly a tangent line at that point. What's the slope of that tangent line? Okay, well, this is the formula I use. Right here, the slope of this line, well, what is it? It's dy dx when x is 3 and y is 4. So negative 3 over 4. Okay? The slope of that tangent line is negative 3/4. And if you find any other point on the circle, you can compute the slope at that point using the simplicity derivative.